right, let's start, right? Again, I'm going to keep it informal. We have two more presenters, right? They're going to go really through the meaty part of the presentation today. It's really the context is that we have done HDP3, early access. The beta has been running for about 3-4 months now, since March. So we are going through the beta early access GFAs. So what I've done is work with Micron, IT, customer as well as vendor, right? And do some real world test cases with SSDs. And that's what we're going to talk about today. So you're going to see both HDP 2.6 as well as HDP 3.0 beta. Quickly, the agenda is going to be introduction, right? And what's new in HDP 3. Quickly, I'm going to kind of tee up and see what's new. And then, of course, then I'm going to be to Greg to go over the use cases and also Mike from Micron IT perspective. Quick introduction again, I'm Sumitra. I'm on the Hortonworks side, running the HDP product management. Also been involved with Vinod and team to launch HDP 3. Greg, introduce yourself.
Greg Kincaid, I'm the Ecosystem Enablement Program Manager for the Micron Storage Solutions Center in Austin.
And Mike.
I'm Mike Cunliffe. I am an enterprise architect, and I work in the enterprise analytics and data team at Micron supporting manufacturing.
Right. Mike is our customer, not like a vendor, but customer that uses Hortonworks technology to apply in Micron IT internally. So it's really coming from actual use case here. So quickly, what's in 3.0? So if you look at the market drivers, why are we doing 3.0, right? I'm not sure if you've seen the slides. It's really containers, agility, faster time to deployment, faster time to inside. So containers is becoming very popular. We're going to allow you to bring containerized workloads to HDP 3 ecosystem. So it can be TensorFlow, it can be anything lift and shift, anything you want. You can just run inside. The benefits are isolation. Any Python scripts you have or libraries, they're all inside of containers. Other thing we're doing is we're also going to containerize our own stack. If you look at HDP, there are like 30 components in there. So we're going to containerize Spark, HBase, some parts of it. Eventual goal is to go through all, but that's a starting point. And the benefit is going to be that Spark release happens every 4 months, right? HDFS happens once in 2 years. So you're not coupled together with one release. You can all decouple HDP, so that's one of the goals. Scale, we are running a lot of use cases these days. That scale is getting out of the roof. So we're going to increase the scale by 4x in HDP 3 compared to what we have in HDP 2.6 with name node federation. TCO, what it really means is instead of having 3 copies of data, we'll have half the overhead, TCO overhead, huge benefit. Deep learning, again, this is being smarter. So we're going to support GPU pooling and TensorFlow tech preview in HDP 3. It doesn't mean that you cannot bring your own TensorFlow version and run containerized in our HDP 3. We'll support that. Security governance, we had it Ranger Atlas for a while. We're going to make sure those are on by default. Means your data lake is no longer, data lake is no longer a swamp. It is a data fabric. So security, Ranger, Atlas are turned on by default. Real-time EDW, so as you know about Hive and Druid, so we are going to turn on ACID on by default in Hive 3. So the HDP 3 like Hive 3, it's going to have ACID on by default. And we're going to have single interface for both your batch workloads and real-time workloads. This is interesting ISB, so again, it's containers. Because of containers, I can bring third party. So IBM DSX, for example, that can be deployed on a single cluster. And then we can bring more third-party apps over time. For the sake of time, I'm going to move fast. This slide should be on our website. This is the latest architecture, right? To see how all this compares. You can go and look at it. Sorry, if you want to take a picture, go ahead. Just take a picture, and I'll move. Okay, it's on our website. This is, I'm not sure it's on our website, but this is an important one. So this shows how important, how big HDP 3.0 is. If you look at how we have evolved, if you look at a version of Hadoop core, it hasn't changed. Look at a version of operational data store, HBase, it hasn't changed. In HDP 3, every version is changing big time, going from 1x to 2x to 3x, right? So it's one of our biggest releases in 4 years, but we also spend a lot of time making sure we go through beta, early access GA to make it more stable. Now, use cases, right? Why we think SSDs are important, and these are 3 use cases we came up with. One is Hive, of course. If you run interactive queries, performance is very important. So we're going to we have done use cases where we have accelerated Hive queries with SSDs. HBase, we have a lot of customers. We have all HBase, all SSD deployment using HBase, especially for real-time workloads. And tiering, this is more like when you have a QLC-based SSD, I mean, very high density, low write, more like a write once, read many times workloads. SSDs are really powerful from a power and cooling, and it's going to be very high density SSDs. So it's a very good use case for active archive and erasure coding. So 3 use cases. Towards a journey, we just started partnering with Micron about 3 months ago, but Micron IT has been a customer for many years. We'll be working on all the 3 use cases over time. But today, we're going to spend more time on Hive part of the use case. With that, I'll pass it to Greg.
So at Micron, we are continually testing methods to optimize big data solutions with Micron SSDs and memory. In evaluating the, HDP3, we asked ourselves, how can SSDs benefit the Hadoop cluster without wrecking the $ per GB profile? So our approach was to add to each node in the cluster a single TLC SSD to accelerate application performance. TLC is an acronym for triple level cell. It just means that the SSD was built with TLC NAND. In the near future, SSDs built with QLC NAND, quadruple level cell NAND, will drive down the price of the $ per GB enough to make all-flash Hadoop clusters more palatable to the masses. QLC is ideally for those applications where you have a write once, read many that Sumitra talked about earlier on the Active Archives 1 application of that. So our baseline was from testing a cluster with 15K hard drives running Hive as an application. The comparison test was done with an identical cluster with a single Micron TLC NVMe SSD added to each node for a caching yarn to accelerate Hive queries. So this is a view of the clusters that we used. In the gray corner, we have a cluster where each node has 12 15K hard drives. In the blue corner, we had an identical cluster, but we added an NVMe SSD to each node of that cluster and used Hive as the application. You can think of the SSD as a cheap memory or an equivalent to an L2 cache. Note that we used a 2 terabyte database with just over 800 gig memory, total memory for the cluster, This was to ensure that we weren't running all of the operations in cache, that we had a minimum of 2-to-1, a 2-to-1 ratio for data to memory. And the results were striking. If you look at the graph here, the gray are the query completion times for the all 15K hard drive cluster, and the blue is the same cluster but with a single NVMe at the node level. What we found is that for the longest running queries, we saw up to a 2.5 times better query performance. And we also found that the NVMe Yarn cache had the maximum impact on those queries that created shuffle. On the average over 92 queries, we found that the single SSD node cluster was 1.7 times the query performance of the all 15K hard drive cluster. And you can expect an even greater performance multiplier when you compare these results to a 7200 hard drive cluster. But what was more compelling is that the percentage CPU time waiting for disk I/O was completely eliminated with just one SSD per node. And that's what you see in the graph below. The top graph shows the percentage of the CPU waiting for each node. Each node has a different color: red, green, blue, and yellow. But just one addition to one SSD in the node, each node of that cluster, you can see that there's virtually absolutely no CPU wait time. So we're just at the beginning of our journey with Hortonworks and investigating how SSDs can improve the performance in a Hadoop cluster. We'll be doing an additional studies, performance profiling, and we'll be publishing those soon. So now Mike will discuss Micron IT's experiences, real-world experiences with HTTP and Hive. Sure. We use compression. No. Good, Mike.
So I'm going to talk a little bit about the work that we did that kind of builds on the work that Greg and his team had did. So we took the SSDs and we took it to LLAP and seen what we could do with LAP cache in SSD. So a little bit of background. We support the Hadoop clusters that support manufacturing operations. We have 2 clusters, one in North America, one in Singapore, to support our global operations. Right now they're sitting at 506 nodes, 28 petabytes of data, and we're a big user of Hive. We have 64,000 tables in our clusters and 10 million partitions. Through the cluster, we managed to get 576,000 jobs a day, and it's a real mixed workload. A lot of it is Hive queries. So let's talk briefly about LAP and the architecture. I know there's been a lot of stuff on it, so I'm not going to go into depth. But the big thing with LAP is the persistent daemons that spin up and stay resident on your Yarn cluster. And then within those daemons is a number of query executors. So the advantage that you get with this is it pretty much eliminates startup cost, right? You don't have to spin up containers and get your stuff out of all the nodes. It's hot, ready, and available. Another benefit of this, though, is now, because they're stay resident, we can add cache. you can have this process manage a cache over the lifespan of multiple queries, because it's not throwaway at the end of the query. The cache can either be in memory or on NVMe's, so you're left with a choice. Which way do you want to go? So let's take a quick look, kind of compare NVMe versus memory, and we'll take a look and contrast that with hard drive. So with an NVMe drive, you get very good latency, 40x that of a hard drive. You get very good throughput, 16x that of a hard drive. And you get a relatively reasonable cost relative to a hard drive. When you look at memory, you get extremely good latency. You 3,000x that of a hard drive, and you get very good throughput, 89x, but it's expensive. So now you're left with a quandary. What do I have? Do I have a small, very fast cache in memory, or do I go with a larger, fast cache in NVMe drives? Well, the only way to tell is to test, so that's what we did. So this is our configuration. It pretty closely mirrors what our production configuration is. We did a 10-node cluster, 256 gig of memory, 40 CPUs per node, one NVMe drive, 3.2 terabyte drive, and 12 6 terabyte SATA drives, totaling 72 terabytes for the node. The configuration that we had for the memory cache, we had 12 executors, 12 threads, and we had a 106 gigabyte container size for the daemon. We set the heap at 76 gig, and headroom was at 12 gig. And then that left about 12 gig for the cache. Now, tuning this was a bit of a black art, and depending on the workload, your numbers may look a lot different, but this is what we found worked best for the TCP DS benchmark is what we were running on this host. When we did NVMe's, we kept pretty much all the LLAP configuration exactly the same. The only thing that we changed was we moved the cache size to 1 terabyte. And then we enabled the memory map, which allowed it to memory map the cache onto the NVMe drive, and then we gave it the path to the NVMe drive. And then, like what Greg and his team did, we also put all the yarn local storage to manage the shuffles across nodes. We also put that on the same NVMe drive. So here's our results. We ran the TPC-DS 1 terabyte benchmark, and we normalized this so a straight run on Hive is a value of 1, and then everything else is relative to that. Pretty much across the board, we've seen that LAP was faster than Hive in all cases, and pretty much across the board, we've seen that running it on an NVMe cache was faster than running it in memory. The performance for LAP was on average 2.6 times that of Hive. And then when we moved it to the larger cache in NVMe, it jumped to 3.7x the performance that we were able to get with Hive. Another way of kind of visualizing this or looking at this is if you were to use like a scale-out model and you ask yourself how much I could gain by adding SSDs to the current cluster. So you look at a cluster that's kind of at our scale, 200 nodes. When you add NVMe's, assuming linear scalability, which you generally get with Hadoop, that's equivalent to adding 80 nodes in performance. So it was pretty striking for us, and as a consequence, we're moving forward, and we've actually started to roll out the NVMe's into our cluster, and next week we should be enabling LAP and start to be able to put some workloads on that and do some testing there as well. That's all I had. Questions?
So I see each node had 256 gigs. Did you try making the LLAP caches 200 gigs instead of 100 and just see what the delta might be?
You can't put the cache that high because it doesn't leave anything for the executors. So we learned a couple things. One of them is we kind of started off with only giving about 100 gig of the 256 to the daemon processes, because initially we were thinking, well, we may run this in a multi-tenant. We may put other things on there. It really wants to consume the box. So to start with, we would probably put all the memory into the Hive daemons. But even if we were scaled up like that, if you went, there was a Walmart presentation, which they did exactly that. They were still only able to allocate about 40 gig to the memory cache and still be able to service their workloads.
And that was a single user TPSDS run that you had the numbers for?
Yeah,
Okay.
one pass monopolizing the box.
Any concurrent numbers? Just curious. Tried 5 users or 10 or something?
No, we didn't
Okay.
run concurrent tests. Mhm.
Anyone else? Okay.
What was your network
10 gig.
and your rack switches, interconnectivity?
Top of rack, 10 gig.
To your spine, if you will, right?
This
node-
all ran in one rack.
I'm sorry?
This all ran in one rack. Our production clusters have 40 gig up, but this was isolated to a single rack.
You had 200 nodes, right?
In our production clusters, our test cluster was only 10.
Ah, okay. Sorry, my bad.
More questions? Come on, it's only 5:12. Yeah.
Why did you choose not to use compression?
In the beta, we went with typically on the team that I'm on, we always stick with default settings, even though that's not optimal. If anything, the settings are always optimized for hard disks. What we were trying to do is to demonstrate if you just add in an SSD, how does that help improve performance? And then on the beta, by default, that was not turned on, and so we just stayed with that. Which we typically do, even if it's production code, we'll always stay with default settings. Because you can get into the weeds in fine tuning something, and that's not necessarily something someone else can reproduce easily. So on our side, that's what we try to do.
Yeah, the reason for that is we want to make sure that the results are repeatable, and Lego makes us do it anyway. So we always use the defaults.
Yeah, and just to give credit to Micron IT, our SDP3 GA is going to happen in Q3. So they are working with beta bits from March. So, so I think that's other factor. I think, but you're talking about arc compression and all this, right?
Talking about the compression that occurs between the map phase and the reduce phase.
Okay. So, yeah,
For the shuffle.
for a shuffle, okay.
Trying to understand, did HDP turn that off at some point in time?
I didn't know that one.
Huge implications.
Somehow I thought you're talking about arc compression. Okay, I don't know
That
that.
has huge implications on your networking, and that's what I'm trying to figure out.
Okay.
And for our, so he was dealing with a 10 gig network. With us, we've got 25 gig NICs, and it goes up to a 100 gig switch.
Yeah, you can reach out to me if that's a default config. Happy to work with you.
I'm trying to understand.
Yeah, visa right. Okay. And sorry, you have a question?
So the general question I had first was, instead of an NVMe, could you just use an SSD?
Absolutely. In fact, we're planning on doing further studies with SATA SSDs as the yarn cache as well. And we'll be publishing those hopefully sooner than later. I would expect similar results when you compare them to the 7200. but 7,200 spinners. I don't want to speculate what the improvement will be, but it definitely will be, I think it'll be better than or comparable to what you've seen compared to the 10K drives. Yeah.
You're using this for transient data. What's the mean time between failure if you use it for other storage?
For the SSD.
That's a good question. I can't answer that off the top of my head.
Because to be honest, that's the thing that most scares me about SSD is the mean time between failure.
The last time I looked, it was 3 million hours, so it was
Yeah.
comparable to spinning disk.
I mean, I used to be an SSD startup. For all use cases in tier 1 workloads, OLTP, it is supposed to last 3 to 5 years with the workloads.
Yeah, the drives are warranted to 5 years.
Yeah. It's not designed for that. I don't
Right.
think I'm going to hit that mean time to failure soon. And I think other thing this is market for them is last year's tipping point, SSD revenue surpassed its hardware revenues. So it's, yeah.
And does Bezos' law also apply to this? In other words, as time goes on, we get more of it for the same price?
That's the goal. Whether or not we reach it, it's another story, but that's definitely the goal.
Any more questions? We can take one more.
One last thing is, when are you announcing these results publicly?
So, well, we just finished the results. It takes us about 6 to 8 weeks to release them. If you give me your card, I'll make sure you get them as soon as they're available.
I'd be glad to, because that way I can buy some more Micron stock.
We'd love that.
Awesome. That's awesome. Anything? Anyone else? Cool. Thank you so much.